This is project 4, video number 1, pencil and paper part. We've got a disc, radius r equals 1 meter, and it's in pure rotation about a vertical axis through its center. It's a horizontal disc, and we're told it's got an angular velocity omega, angular acceleration alpha, considered positive as viewed from above, and they want us to find for a point anywhere on it, say some distance r out from the center, find out what the magnitude of the acceleration is, and make a graph of it as a function of r. The magnitude of the total translational acceleration, which consists of a centripetal part and a tangential part, a sub t. The tangential part is just r alpha, and the a sub c is r omega squared. Okay, so I'm actually expecting just a linear function of r. Oh no, we got that. Yeah, I think it's going to be a linear function of r that depends on alpha and omega, and the values are going to depend on. It'll go from 0 out to some maximum value of r, and the values are going to depend on just what at and ac are, the max value that you get at r is equal to 1 meter. Okay, so it looks pretty straightforward. Let's go ahead and calculate the total. I think I'll put these in red since I got one red in the diagram. So a sub t, vector addition diagram for a sub t and a sub c looks like this, where they're at right angles to each other, so the total acceleration is just this. That's the total translational acceleration in magnitude. Well, it gives magnitude and direction if I do the vector addition, but they just want the magnitude. So I'll take a is equal to, from that triangle, a c squared plus a t squared, which is r omega squared plus r alpha square root. And I can indeed factor an r squared out of from both terms, and then take it right outside the square root where it becomes an r. So we got a is just equal to the square root of omega to the 4th plus alpha squared times r. So that's interesting. Our graph, let's make sure I got the graph. Creates a graph of the magnitude of the translational acceleration of a point on the disk versus the distance that the point is from the center of the disk. Values that distance from 0 to 1. So it should just be a straight line passing through the origin, where the slope is given by this combination of omega and alpha. And the algebraic sign doesn't matter of either one of them, whether it's going counterclockwise and slowing down. It's just the magnitudes, because they're getting squared, so the algebraic sign goes away. Okay, as part of your pencil and paper solution, provide yourself with a crude check on the code by solving the magnitude of the translational acceleration at distances of 0.5 and 1 meter. It's for this special case. So our function should work for any omega and alpha, but I want to check it with this special case. So I'll call this test case. alpha is equal to, for the test case, 12 radians per second squared. I'll put down the omega first. Omega is equal to 5 radians per second. And alpha is equal to 12 radians per second squared. So at R equals 0.5 meters, A equals, by the way, let's check the units of this. This is radians per second squared, which we can think of as just 1 over second squared. Square that, it's 1 over seconds to the 4th. This is radians per second, which we can think of as 1 over seconds, as a radian isn't a true unit. Bump that up to the 4th power, we got 1 over seconds to the 4th. So inside the square root, we got 1 over seconds to the 4th. Take the square root of that, we got 1 over seconds squared, times R in meters. We got meters per second squared, so the units do work out. Alright, that's a nice check as well. So at that, we got 5 radians per second, quantity squared, plus 12 radians per second squared. This was quantity to the 4th power. This one's quantity squared. And then all that times 0.5 meters. So at 0.5 meters, A is equal to, go ahead and evaluate that on the calculator. Then I get 13.8625 meters per second squared. And I didn't show all the sig figs on the way through, but let's get to 3 sig figs. And then at R is equal to 1 meter, by radians per second, quantity to the 4th, radians per second squared, quantity squared, all times 1 meter. So that should be double what we just got, but I'll plug the whole thing in again just to make sure. You get A equals 27.73 1 meters per second squared. So that's our other answer. Also good to 3 sig figs there. So I get something to check the code against, make sure that for the case where omega is 5 radians per second, alpha is 12 radians per second squared, we get about 14 meters per second squared at the halfway point on the graph, and roughly 28 meters per second squared at the max. Alright, so what do we want this code to do? Let's say accept argument omega and alpha. Just want to check, make sure get the order right. It takes 2 arguments: the angular velocity of the disk and the angular acceleration. I should say in that order, but okay. The order isn't really going to matter in the end, but that's the order that they were given us, so I'll take them that way. evaluate, return oh, I know. I can't just, we're not returning anything. It's, go, let's say R equals linspace 0 to 1 in 101 steps, and then A equals, I go square root of omega squared omega to the fourth, I think it was. Omega to the fourth plus alpha squared, and then times R. Let's see if I got that right. So the square root of omega to the fourth plus alpha squared, and then the quantity times R after you take the square root. Alright, I think that looks good. And then plot. There's got to be a lowercase p plot R comma A, and then clean up the plot, and I think that'll be it. Alright, so that should be straightforward. Let's call that a wrap for project 4 video number 1.